Are you recording? Yes.
Yeah, I started the recording. Thank you very much, all. It gives me great pleasure to welcome Professor Kyle Riding, Professor of Civil and Coastal Engineering at the University of Florida. He is the University of Florida Foundation Professor. He has a master's and PhD in civil engineering from UT Austin in 2004, 2007. He's highly active in ACI, RILEM, Journal of Materials and Civil Engineering. All of us in the field know him very, very well. His work has won numerous awards, including the ACI Wason Medal, ACI Young Member Award, and he was recently elected as ACI Fellow. He's done a lot of work on a wide range of topics: concrete durability, sustainability, CO2 footprint reduction, UHPC, concrete construction, etc. And he's going to talk about ultra-high performance concrete, new methods for strength and performance. So thank you very much, Dr. Riding.
Okay, well, thank you for having me, and get to talk about UHPC today, which is a topic I love talking about. This is some work that we're doing for the Florida Department of Transportation, and acknowledge the co-authors on this, Megan Voss, one of the PhD students on it. She's now an assistant professor at University of Evansville. Raed Al-Rashidi just successfully defended his PhD. Dr. Ferraro and Hamilton, and Dr. Harley, he's a professor here in electrical engineering, and Daniel Olivi, he's a PhD student in electrical engineering that we're working with on some of these NDT methods. So why are we talking about UHPC? Well, a lot of it comes down to durability. Here's a picture of a bridge in Cedar Key, Florida, from about 2 years ago, and you can see within a couple months, this is what it looked like. They are having to reconstruct it because of corrosion in the saltwater environment. So UHPC is viewed as a material that could really extend the life of our infrastructure, could give us very, very long service lives for our infrastructure in these marine environments. And so there's a great desire to be able to use this material for that purpose in the state, instead of materials like stainless steel or other materials for corrosion resistance. So UHPC PCA says that it's a high strength concrete with specified durability, tensile ductility. That's really important, the ductility and toughness. And fibers are generally included to achieve specified requirements. So typically we're using steel fibers. A typical dosage is 2% by volume of very small, narrow fibers. Typical one would be like a 0.2 millimeter diameter. So these are very, very fine steel fibers that are used to give it that tensile strength and ductility. We often want these materials to be strain hardening materials, and so you do need those fibers to get there. These materials also have very low water cement ratio, we'll talk about in a second. The tensile performance can allow you to reduce the amount of reinforcing bars, and helps you get to longer members, up to say 300 feet. They're working on right now. You can optimize the geometry. Maybe you can cut the member size in half to use less concrete. You can even reduce shipping costs and reduce the crane size by making the members lighter by reducing their weight because of the high strength. So there's a lot of opportunities here that are provided by use of ultra-high performance concrete. Here is a picture of a bridge in Medellin, Colombia. It's a pedestrian bridge that was built a few years ago. It was built on a cost competitive basis against a steel pedestrian bridge. It's built in segmental construction style. And you can see it's a very beautiful bridge over a very busy street, and was done at a significant cost savings to that of the equivalent steel bridge. So you can do this in a cost competitive way with these ultra high performance concrete mixtures. Right now, the most common use of it is for connections, to connect together precast members on site to give you high durability. This is where a lot of the problems are with bridge decks, is with these joint sections. So if you can use a very high strength material that gets excellent bond between the materials and isn't going to give you cracks at the location where you have these high stresses at these connections, it can really prove valuable there in extending the life of your infrastructure. This has almost become a standard detail, basically a standard detail in New York State. Florida, we've tried a couple bridges here with this detail. Piles, I think, is one of the interesting first member types that can be done and done cost competitively in Florida. This picture of a square pile being made, but you can optimize the geometry in octagonal shapes that are hollow or H piles, and also make it really cost competitive with that extra life that you get out of this really highly durable material. So it can make it cost competitive when you compare it against using stainless steel. Here's an example of a test pile that was driven, 100-foot test pile driven in Leesburg, Florida. You can see after they tried to beat the snot out of it, and you can see hardly a chip on it after it was done. In fact, it did so well, they ended up, the wood cushion they used to drive the pile caught on fire. You can see some of the smoke coming out. When they were done, they took it out, and you could see a big flame erupting out of the wood cushioning that they use on this, because it was so much energy that they put into it and driving it, and still very little damage. These are very durable materials, high toughness. So how do we get UHPC? Well, we can go back to our original Duff Abrams. I love going back to Duff Abrams. First, I love his name, Duff. Reminds me of The Simpsons, but we come back to the water to cement ratio. So how does the water cement ratio work? Well, the closer you compact your solid particles together, the less porosity you're going to have, and you're going to improve your gel space ratio. And really it's that gel space ratio that's going to give us really high strengths for compressive strength. And so we use low water to cement ratios, very low water to cement ratios. Well, low water cement ratio is great, but there comes a certain point where it's hard to place. So how do we get to these very low water cement ratios? Often they're at 0.13, 0.15 in that range. How do we get to that point? Well, the answer is particle packing. You get your particles very close together by optimizing your particle size gradation. So if for instance, this is your mono-sized particles, let's say this is your sand, you can fill it in with cement particles that are a little bit smaller, and then you can use silica fume, for instance, to fill in even more space with solid material. That every space that you fill with solid material is space that you don't have to fill with paste or with water to fill in that space. And that water, that if it doesn't react, is just going to provide porosity and limit your strength. So we need to use very good particle packing. So this often means using high amounts of silica fume and many times ground quartz, silica flour, and optimizing that particle size with your cement and with your sand. These mixtures don't have any coarse aggregates typically. It's just sand, cement, and then different SCMs like slag, silica fume, and ground silica flour. Also, these mixtures require very high doses of super plasticizers. When you start buying it by the barrels to be able to use it, oftentimes it's going to be an order of magnitude higher super plasticizer dose than you would use in a typical SEC mix. And this is what can give you this very high strength and durability. They're also oftentimes steam cured to give high strength, to really get as high a degree of hydration as you can out of these systems. Okay, so let's talk about it. So it's, we like to talk about strength, how many PSI is it in compressive strength, but really what gives UHPC makes it such a wonderful material is its tensile properties. In reinforced concrete design, if you remember back from your reinforced concrete design class, we typically neglect the tensile strength of the concrete and rely on our reinforcing steel bars and pre-stressing to provide the tensile forces that we need for equilibrium for our structural members. Well, with UHPC, we can actually get strain hardening performance and toughness that allows us to start to rely on these the tensile properties of the UHPC. And so it's these steel fibers that do that. So if it's the tensile strength that really opens up the opportunities to have very low cracking or eliminate or very small cracking, and to allow us to reduce some of our reinforcing steel bars and get good efficiency out of our material, we need to be able to know what the strength of our material is in tension. And we need to be able to verify that the fibers that provide that strength are where we want them to be and in the direction we want them to be, because a fiber is only going to reinforce a crack if it crosses the crack, if it's going to provide bridging across the crack. If it's in the same direction as the crack, it's not going to be able to provide you any reinforcement against that crack. And so we need to make sure that our fibers in the direction that we want them to be. Okay, so those are a couple of the main issues that I'm going to talk about today. Is how do we validate the tensile strength and validate the fibers that give us that in situ in our construction members. Okay, so there are really three categories of tensile test methods out there for concrete. There's direct tensile tests, and there's a variety of flavors of these out there that you can use, where you basically pull in direct tension your sample and you measure its stress and strain, just like you would with a steel coupon or anything else. The next category is bending or flexural tests, where you place your sample in bending and you try to then back calculate your stress strain curve from the flexural load displacement curve that you get. And there's some assumptions that you have to make then about the shape of your stress strain curve if you're going to do that. And that's one of the drawbacks of these flexural tests. And then the last category is splitting tests. And splitting tests, think of like your Brazilian splitting tensile test. That's the third category that you have. Okay, so here's an example of direct tension test. This is what we've been running in our lab. It's very good because you get excellent stress strain results. You don't have to do an inverse analysis or assumptions, but it's very expensive, the equipment, and a lot of the samples when you test them fail. You typically will make 6 samples and hope that 6 of them turn out well. The next category, flexural test, ASTM-C 1609 is the most common one in the United States. It's used for that, and you get a load, a bending stress displacement curve that you then have to then back calculate to get your stress strain curve from it. That inverse analysis uses assumptions. The French standard has a good procedure for doing that, but there's still all of these assumptions in there. And that's one of the downsides. Now, you still need a closed loop testing machine to do this test, and that equipment is not widely available, but this test is more widely available than direct tension for UHPC. And it is much easier to run, but still it's the equipment and the knowledge it takes to do this with the assumptions. It makes it not ideal for quality control. Maybe for qualification, direct tension and flexural tests can work really well for that. But when it comes to actual quality control in a plant, in a precast plant, neither one of these options are very desirable. The equipment just doesn't exist in the precast plants. The third test method that I want to talk about today is a simplified or modified splitting test. It's a double punch test. So if you come back and look at this, you basically put steel punches on the top and bottom of a concrete sample. And as you compress the steel punches on your concrete cylinder, it's going to form cones of failure underneath the punches as the steel punches dig in the concrete. And that's these punches are going to form these cones that push apart and split your concrete sample. Okay, so for a double punch or modified double punch test that we've been working on and that I'm going to talk mostly about today, you get post-cracking data. You do get a toughness data, but you do not get stress strain data. This test isn't standardized, so it's something I'm going to talk about today, how we've modified the original double punch test that was developed in the 1970s to be able to give you enough information that you can use for quality control. Maybe not qualification. We're not trying to get a stress strain curve out of this, but at least for qualification. So if you think about a tensile testing that you would have for quality control in your precast concrete plant, the quality control test has to measure toughness and ductility, right? Not just the peak strength. I can get extremely high peak strengths out of a UHPC sample with no fibers that gives you no toughness. Okay, just because of the very high strength of that cement paste holding it together, I can get very high strengths that would fail brittly in a concrete member. We don't want that. We need a measure of the toughness and ductility. So our ideal quality control test needs to be able to characterize the peak strength, also give us the toughness or ductility. We also need to be able to perform this test with commonly available equipment. You're talking in some cases $50,000 for a closed loop testing machine that could run the 1609 flexural test. And that's money that most labs don't want to have to spend. And this is hindering the use and development of UHPC members in practice. Also, it needs to be simple to perform, easy for technicians to be able to do this. Okay, so our ideal test method, we compared these three test methods in order to see how they perform and see if we could use this modified double punch test for quality control of UHPC at the plants. And so we performed these, or on the same batches, we compared these three tests. So let's talk about how we've modified this double punch test. The original double punch test was developed in the 1970s for plain concrete. It was developed as an alternative to the splitting tensile test, but it was adopted for ultra-high performance concrete in the Spanish standard, the UNE standard, and it uses a closed loop test. You need to be able to control the machine displacement very precisely in the Spanish test. And then you measure the circumference change with using basically a chain wrapped around your concrete sample that can measure very precisely the expansion radially of your concrete sample as it fails. So we have modified this test to be able to do open loop, to test it in open loop displacement control, which is basically what your standard compression machine used for concrete compression tests can do. And then instead of requiring that expensive, it's about $6,000, that extensometer to measure the circumference, we've replaced it with measuring the crosshead displacement of your compression machine using just a simple dial gauge, a $100 dial gauge. And so it's much simplified, and you just basically measure pairs of crosshead displacement and load for this. And we've looked at it, basically your displacement rate, load rate, they're pretty linear, up until the very end of your test. And so you get pretty good comparison with these machines. These machines tend to be basically open loop displacement control, these compression machines. Okay, so basically after your peak strength, after you start to get some failure of your sample, the question is then your sample can release some strain energy, and if you use plain concrete, you would get a sudden release of energy and a sudden change in strain very quickly. And so that would create an unstable system having that energy released. With ultra high performance concrete, however, you don't get that. You have a ductile behavior where you don't get that sudden elastic strain release of your material. And so there's a study done in Brazil where they looked at the instability with the double punch test at open loop versus closed loop. And they found that open loop systems gave conservative values. Okay, conservative, that's good. That were slightly lower in toughness than closed loop systems. Now, this study was done for materials that were low in fiber content compared to what we use in ultra high performance concrete. And so the ultra high performance concrete we think will do even better, but it found that the differences between the load at crack and at 0.5 millimeter of axial displacement from that, there was no statistically significant difference from the ones obtained in the open loop machine and the closed loop machine in that test. And now, since we're using even higher doses of fibers than they are, we expect this not to be a problem based on their study. That instability basically goes away as you increase the fiber content. So we're very hopeful that we can modify this test to allow just axial displacement measurements, because the axial displacement measurements, once you get cracking, they correlate linearly with the circumferential displacement. So you get a very linear relationship after you get that first crack. So we're able to simplify the test, going from circumferential extensometers to a linear, say, string potentiometers, and then simplify it further by doing just manual points. So we looked at our results by first looking at the continuous data of the axial displacement versus the load. And we looked at discrete values and looked at what happens if you only were to take a point every 0.05 inches of displacement, or every 0.025, or every 0.01 inches. And we found that if you were at 0.025 inches, taking a reading every 0.025 inches of displacement or greater, you only have about 1.5% error caused by taking discrete values in your toughness rather than your continuous values. So you're basically approximating the shape of that continuous curve with these discrete values, and the error gives you only about 1.5% error from that approximation. So we felt very good that was a worthwhile trade-off for the simplicity that you gain from that, from using those discrete values. So this showed us that we could take values at discrete points manually by just reading the dial gauge to look for a specific displacement, and then write down the load at each of those displacements. And then you can calculate the toughness as the area under the curve of that stress displacement curve. One thing that we did have to do, though, is you do have to set the displacement equal to 0 at a certain point, and that's because of seating of the punch. So if you put the punch on top of your sample and there's a little bit of roughness of the sample, that punch has to basically crush any local roughness to smooth it out, to be able to give you a consistent place of where to start your load displacement curve. So we found that at about 10,000 pounds of force, that was enough to overcome any surface roughness that you had in your sample and give you consistent results after that with your load displacement curve. And in fact, we did a ruggedness study according to the ASTM standard for ruggedness studies, and we looked at the effects of grinding our samples versus using a rough finished sample. The punch offset, if you offset the punches 5 millimeters, we looked at the loading rate, going a slow loading rate versus a fast loading rate. And we found that none of those parameters were statistically significant. So you don't need to grind your samples in order to get good results. The one thing that we did find, though, is that the way that you make your sample, the way that you fill your 6-inch diameter, 6-inch tall cylinder, does make a significant difference in the results. Very big difference. And I'll talk about that in just a second. After we did this ruggedness study, we also looked at the machine to look at the stiffness of the machine. How does that affect results? So we have 3 different compression testing machines, open loop testing machines in our laboratories. And so we made 18 samples and tested 6 with each of these testing machines, and found that the coefficient of variation was fairly low, and the statistics told us that it was not statistically significant in the machine. And so we felt pretty good about being able to use this on different compression machines, that the stiffness of the machine with UHPC wasn't going to impact the results. Because it's a ductile test, or a ductile material, and doesn't respond poorly when you get cracking, because it doesn't have that sudden elastic release of energy. Okay, so we looked at filling up our samples with a scoop and with a bucket. And what we found that the scoop filled samples had much higher tensile strength results than our bucket filled samples. So we thought this was curious. And so we did computed tomography scans of the samples. These are slices of our samples, or wedges of our samples, to look at the fibers and how the fibers were oriented. So the fiber orientation, you can see here the fibers in these computed tomography scans. These are basically X-ray images, kind of like a CAT scan, where you can see inside the sample and see the fibers. What we found was you had extreme preferential orientation in the fibers, basically making them much more horizontal if you filled them up with a scoop, where you do one scoop at a time, versus if you take a bucket and you just place it all at once in your sample in a rapid manner, you get a much more random orientation of your samples, and it gives you more conservative values. And the reason why is because if you have a sample that you're filling with a scoop, you're filling it layer by layer, and those sample, you're basically allowing the sample to find, since it's a self-consolidating material, it goes, each layer forms its own little mini layer, and the fibers, as they flow in that mini layer, are going to align themselves with the direction of that flow and are going to become more horizontal as you fill it up slowly with the thin layers with a scoop. However, if you do it with a bucket, you get a much more random orientation because they're not having to flow during that time of each thin layer being placed. And this was confirmed by our computed tomography scans, why you're getting such high results. So you have to make these samples very quickly by filling them in one motion rather than using a slow filling with a scoop. Okay, so if we looked at our direct tensile testing results, when we're comparing our direct tension results to those of the flexural tests and those with the modified double punch test, there's a couple things that we wanted to look at. We wanted to look at the area under the curve, which is the toughness of our direct tension results. We also wanted to look at the stress as specified strains and the maximum stress. So those are the three things we looked at. So particular strains, like at 0.05 strain, we looked at that, and 0.01, for instance. We looked at the maximum strength of the material, and we were able to compare that to our results from different tests. Okay, so if we compare our ASTM C1609 flexural beam test, bending test that you have, to the direct tensile stress, you do get a halfway decent correlation, but there is some scatter, and that's not necessarily surprising with any measure of tensile strength. Tensile is more variable than compressive strength. That's well known in the industry, but there is a decent relationship with the maximum stress. Part of this could be based on the cracking strength. If you have a material with low fiber content, its peak strength is going to be its cracking strength, and that's going to be much more variable than when you have the fibers in there. We looked at comparing mixtures with our direct tensile test to the flexural toughness. So that's with our flexure test, you can see you get a much better relationship with the toughness results, and that's because it's a little bit more consistent rather than the peak strength, which is more dependent on just that value. So then we compared also the strain or the stress at 0.05 strain in our direct tension test to our flexural stress at L/600, which is a common parameter used in the 1609 test, and you find very, very good correlations there between your flexural test and your direct tension test. Well, we looked then at the double punch test, and you see very similar, our squared values, similar type of relationship with the direct tensile stress. But one of the differences you see is that the equation for our best fit is very close to 1 to 1. So meaning that we're getting the same order of strength out of the double punch test that we get out of our direct tension test. So we thought that was really interesting finding that unlike if you go back to the flexural test, you see much higher bending stresses out of the flexural test than you do out of direct tension, but we don't see that with the double punch test. They're very similar. If we look at the toughness results, we see very good correlations between our double punch toughness and our direct tensile toughness. Very good relationships there that we're able to see. Nice correlations. And then if you look at the double punch stress at 3.6 millimeters, you see a very good relationship to that at the 0.005 strain with your direct tension test. So we feel very good about the ability of this test to characterize the strength and toughness of your material. Is it going to give you a stress strain curve that you may want for design and for mixed qualifications? No, but we think that it has a very good promise for quality control tests. So if we look back at our ideal QC test for tensile strength, we see that it has to be able to accurately characterize the tensile strength. And we're able to do that with the direct or the double punch test, the modified double punch test. Does it provide a measure of ductility or toughness? Yes, very nice correlation with the direct tension test. Can it be performed with equipment commonly available? Yes, and I'll show you a little bit more about that in a minute. Is it simple to perform? Our tests were run by undergraduates with a little bit of training, 10 minutes or so of training typically, but they're able to run the test very easily. It's similar in magnitude of difficulty as maybe an elastic modulus test, maybe a little bit simpler than that. Okay, we've also done a double punch study, and University of Miami was kind enough to participate in that test. So if we look at what was done with the round robin study for this double punch test, we made 3 different material or mixtures, A, B, and C, with different fiber contents and slightly different mixed designs to give us direct or different tension results. So different fiber contents, 1.5, 2.5, and 3. We also made some practice samples for labs to be able to practice the test. And if you look at the results, what you find is that the peak stress, you have about 10, 11% coefficient of variation for the peak stress. That's just slightly higher than what you get for, say, compressive strength. And then toughness, we're at about 17% with materials A and B. That's the same level. I believe it's about 17% coefficient of variation for one of the measures of toughness for the ASTM C1609 flexural test. So we're in the same order of magnitudes, very similar values of coefficients of variation for our these material A and B that we test in the round robin study as what you get for the flexural test. So that's very promising. And for our material C, what we found is a little bit higher toughness, up to 30% coefficient of variation. But if we look at why that happens, our last 5 materials that we tested had much higher strength than the other 2. And what we believe happened is that the material started to stiffen up as we were placing the samples. The last samples that were placed, those last 5, started to have additional fiber orientation because of that stiffening and because of the way that the samples were placed because of it, and because of the way the samples had to be sampled out of the mixer. So if you take those last 5 away, then you end up with basically coefficient of variation values very, very similar to the first 2 materials. So we feel very good about the coefficients of variations of these materials. Okay, so what about fiber orientation and distribution in the members? So we feel like we have a good test now for quality control of our samples for the plant, so that you can actually measure in the plant your tensile properties without having to send your samples away to a fancy lab in Chicago or some other fancy lab with the closed loop test equipment that can do ASTM C1609. But if you're making a member, you're not just relying on the overall average materials that came out of the mixer to have good tensile properties. You're also relying on them in the member to be where you want them to be, to not be segregated, not have all the fibers fall out where you're placing it and go to the bottom of the member. You're also relying on them not to orient themselves as they flow down the bed to align themselves in the direction of the bed if that's not what you want. So you need to be able to in situ quantify the fiber orientation and distribution in the members to be able to have good confidence that your member is going to have good performance in service. Okay, so this is a method that we've been working on with our electrical engineering friends, Joe Harley and Daniel Alibi. And in this method, it's basically, it uses magnetic inductance. So if you take a magnet and you, if you look at the magnetic field from this bar magnet, this U-shaped bar magnet, if you have a fiber that is in the same direction as your magnetic field shown on the left, you're going to get a high inductance measured. Okay, you're going to pick up a high inductance with your magnet. If you have a fiber that is perpendicular to that field, you're going to measure a low magnetic inductance. Okay, so that's the physical principle behind it. You can see our bar-shaped magnet with the windings. You have the magnet there and then the windings around it, and you hook up those windings to an inductance meter, and you're able to measure the magnetic inductance that you get from this system. Okay. So the U-shaped magnet gives a highly directional magnetic field that you're able to then look at the fiber orientation. We've done studies with Consol to model the magnetic field to try to optimize this system. And we found, for instance, that if you only have windings around the legs instead of having it on the top also, you get magnetic field leakage on the top of the bar magnet that reduces the efficiency of your magnet. Another example is pancake coils. Those are popular in magnetic inductance, and you found that you got suboptimal measurements in the models from that. And so you get the best directionality and field by having a bar magnet, U-shaped bar magnet with winding on all three sides. We also found from the simulations that you get better readings at the lower frequencies. So the lower the frequency, you're going to end up with higher sensitivity. And there's theory that all supports that, but we did model it. Okay, so one of the things about magnets that I'm sure you're all aware of is that the magnetic inductance, it changes with distance from the steel, from the magnetic material. It decays exponentially, basically, from that with distance. And so this is a limitation of magnetic readings. Any magnetic reading that you have of a sample is this decay with distance from the magnet. And so we're a little bit limited to about the top inch of the concrete with this to be able to see with our magnetic inductance the top inch. The magnetic inductance for UHPC, you get a very linear relationship. In our laboratory samples, we made laboratory samples with different fiber percentages and measured the magnetic inductance change when you're above when your magnet's on top of the sample, and you get a very linear relationship in the magnetic inductance change, giving us hope that you can calibrate and get the fiber percentage. To get the orientation of the fibers, basically you use two magnets that are perpendicular to each other. So you have one that we call perpendicular, and that's perpendicular to the direction that as you move the magnets along the member, it's gonna be perpendicular to that direction, and the other is parallel. And we've had several iterations of this design to try and optimize the design. Here's one of our systems where we 3D printed the case to hold the magnets in place, and then you have a wheel sensor, a position sensor to measure your distance that you move along your beam. So you basically roll the sensor across your beam, and that'll give you the position of the magnets on the beam, and it will give you the magnetic induction of the perpendicular and parallel. And so it's the ratio of the perpendicular to the parallel magnetic inductance that gives you the fiber orientation. Okay. So we did these scans in the lab. We found very good results. So we took it out to the Florida DOT Marcus H. Ainsley Structures Lab in Tallahassee, where they have several ultra high performance concrete structural members that have been made for tests out there, structural tests. In the boneyard, they have some octagonal piles They have some square piles, H or I piles that are there. And they even have a hybrid UHPC SEC girder, where the ends of the girder were made out of UHPC and the middle was made out of just self-consolidating concrete. There's also a box beam that we tested as well. Okay, so if we're looking at the H pile, you can see the directionality here, the X, Y, Z direction as you move along the beam. So in this beam, for this H beam, we scanned along the web of the pile. We call it an H beam because of the orientation it was in the yard. And what we found is as you move along the beam, you get this change in inductance as you move along the beam. And we went back and we thought that was kind of curious. So we went back and looked at the actual casting of that beam. And what that beam that they used, the SEC mix for it, actually was a very fluid mix that we think was prone to segregation. And these H piles or H beams, a previous student, graduate student at UF, had actually cut out samples from it to do flexural testing on. And the student actually found differences in the flexural strength of the UHPC, depending on if it was at the top or bottom of the beam when it was being cast. And that indicated high amount of fiber segregation in the sample. So what we think happened is as they placed the concrete down the chute, okay, if you were right there where it was being placed, you had a lot of fibers that would be at that location. And as the UHPC had to flow along the forms, you got less and less fibers as you went along as those fibers segregated. And then when they would move over 10 feet to place the chute at 10 feet along, you would get that pattern repeated. And that really, we think, matches up well with what we see in the data here. Okay, so that's great. We see these differences in practice in the inductance measurements. So that gave us hope that we could get those measurements. So we looked at a comparison of the computed tomography results. We took 15 different cores from these structural samples, the box beam, the piles, etc. And we did computed tomography on these on these cores to quantify the fiber orientation and quantities from those CT scans. We kept track of the orientation of the cores when they were in the beams so that we could track that orientation through the process. And so when we got those scans, you have to be able to, in order to get the fiber percent, you have to be able to adjust the grayscale of your computed tomography images to say what's a fiber and what's not. So what we did was we took 50 different fibers from that same manufacturer and did optical microscopy to measure the diameters of those fibers, got a histogram of the fiber diameter, and then we're able to, we basically use that to match up the grayscale required to match the fiber thickness in our scans to that of the histogram measured. Okay, so we were able to get good fiber quantifications of these scans. We also only looked at the top 1 inch because we know that our magnets can only look at the top 1 inch because of the way that magnetic inductance signal decreases with distance from the magnet. So we only looked at this top 1 inch. What we found is if you take the ratio of the fibers in the perpendicular direction to the parallel direction, that ratio, and you compare it to the magnetic perpendicular to parallel ratio, you get a very high correlation in these. This is about as good of a correlation as you're going to see. So we were very, very surprised, delightfully surprised actually at the ability of this method to quantify the fiber orientation. Now, we understand that we're only doing this at the top inch, but our thought is right now there is nothing out there to quantify non-destructively the fiber orientation. This allows us to at least get the top 1 inch. And our thought is if you can get good fiber orientation in the top 1 inch of your sample, then the probability of you having good fiber orientation throughout the thickness goes up dramatically. So we feel good about that. When it comes to the fiber percentage, it's not quite as good. And the reason why is we did a lot of investigation of this. What happens is if you have if you have your magnet that's on your top of your sample, and you have fibers that are vertical instead of being in the horizontal plane, those fibers that are vertical aren't going to be measured as strongly by the magnet. And so it's those vertical fibers that give you problems with fiber percentage. Now we can still get a rough idea of the fiber percentage, and we can tell you if you have areas in your beam that you're having segregation problems. So that's very helpful. We still think it's very helpful for that. But we're currently working on ways that we can optimize this magnetic method to better characterize the fiber percentage. Okay, so with that being said, just some conclusions about this. From this work, we now have this modified double punch test that can be used for quality control testing in precast concrete plants or other placements. So it's something that you can actually have people at your plant running. You get that immediate feedback instead of having to wait for results from one of our friends at the testing labs that you have to mail the samples off to. And who knows what will happen if you mail samples off, if they'll get lost or if anything else happens to them during shipping. And we know that we get similar coefficient of variation as the flexural test anyway. So we feel good about that. It's available. It can be used with common available equipment at these labs. And we know that because the round robin study that was conducted, there are 13 different labs that participated between the different materials, and they had a wide range of compression machines with varying capacities and different operators running this test. So we feel good about that COV based on all of that with different machines that's commonly available. Also, we feel like we have a very good method for non-destructive evaluation of the fiber orientation and structural members. We're still doing a little bit more work on the fiber percent, but just being able to get the fiber orientation we think is very handy. There's a lot of people working on methods to try to optimize fiber orientation to say concentrate the fiber direction in one direction to get the maximum value out of their fibers. There's other people that want random distribution of fibers. I fall more into that category because oftentimes if you're doing a long line pre-stressing like a pile, the concrete's going to flow in the direction of the pile, which is the direction your pre-stressing is in. You want the fibers to be in the perpendicular direction to the pre-stressing, not in the direction of the pre-stressing. It's already going to be in compression with the pre-stressing, so it's not quite as valuable. So we feel like we have a good method for that as well for non-destructive testing. Technologists, Florida DOT for funding the work, and we've gotten a lot of great advice from Steve Nolan and Dale DeFord from FDOT. Acknowledge their work, and Christina Freeman from the Structures Research Center for helping give us access to the UHPC structural members, and also for arranging for FDOT to take those cores for us. And then the round robin participating laboratories, we're very grateful for their participation in this round robin testing. So with that, I'll leave you with a picture of UHPC that you may be familiar with in Miami. You may recognize the Aventura Mall and the ductile that was used on the Louis Vuitton store there. So hopefully that makes you feel a little more at home rather than in our Gainesville pictures that I show you. And from that, I guess if we have time for questions.